Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq Ikmal bin Muhammad Nazir. My metric number is CD240195. I want to present about my static project, and I will be presenting on the section method in structural analysis and the types of truss bridge. Let's dive into how this method helps in determining internal forces in truss structures and explore the different types of truss bridge commonly used in construction. Explaining about introduction, the section method in structural analysis provides a practical approach to determine internal forces in truss members by cutting through a selected part of the structure and applying equilibrium equations. This technique, unlike joint methods, simplifies calculation by focusing on specific sections to quickly find axial forces, making it an efficient solution for analyzing complex trusses. Next, for more explaining, the process involves verifying stability, calculating support reactions, and strategically choosing a cut section that minimizes external forces to solve for unknown axial forces through free body diagrams. A notable advantage is its historical significance in designing truss bridge, which rely on combinations of tension and compression to support loads, making this method ideal for evaluating efficient designs like Pratt, Hu, Warren, and Baltimore trusses. Next, about types of truss. Pratt truss, known for its diagonal members that slope towards the center of the bridge. The Pratt truss efficiently handles tension and compression, making it a popular choice for bridge construction. So the Pratt truss is recommended for construction. Second, Warren truss. Featuring equilateral triangles, the Warren truss offers a uniform distribution of loads, which makes it highly efficient and cost-effective in modern bridge design. Third, Baltimore truss. An evolution of the Pratt truss, the Baltimore truss incorporates additional members to handle increased loads and longer spans, commonly used in railway bridge. And next, Hu truss. The Hu truss has diagonal sloping towards the bridge ends and handles compression better, making it suitable for longer spans and heavy loads. And lastly, about K truss. With its unique K-shaped configuration, the K truss reduces buckling and evenly distributes loads, providing stability and strength for long span bridge. Thank you.
Assalamualaikum, my name is Ahmad Ansar bin Azman. My metric number is CD240314. So I'm going to explain about problem statement of truss. The first one is structural balance, which is to achieving an optimal balance between strength, durability, material efficiency, and cost. The next one is external loading, which is considering static and dynamic loads such as dead loads, live loads, wind, and seismic force. The next one is material properties, accounting for material stiffness, elasticity, strength, and resistance to deformation. Size and weight of the structure, which is the largest structure requires stronger and heavier material to withstand internal forces. The next one is supports and boundaries conditions. The type of support and boundaries constraint affects force distribution within the truss.
Okay, so for the method of joint, so it must be work from the side in the middle of truss. So the first step is we will determine the support section if it requires. And the second, we must draw the free body diagram of the joint. So based on truss, we can see that there are many. We must write the balance equation from each joint, which is the total of Fx equal to 0, and the total of is
Fy
zero
is
false
equal to
members,
0.
and the third one
And
is
the last one
method of
is
section.
we must calculate the equation from join to join.
Assalamualaikum.
Second is zero false members. So how we need to identify it is 3 steps, which is first is if the joint is applied by force or become support reaction, and the second is if the members are non-collinear, and the third is if the members are not parallel. There are 3 cases to identify the zero force member. So the first case is if exists just 2 non-collinear members in a joint, so they will become a zero force member at that joint when no external load on it. And so for case 2 is if the 3 members meet at a joint and the 2 is collinear, then the third must be directed perpendicular to the other 2 members, so it will become zero force members. So for the case 3, if a joint there are not non-collinear members and no external force is acting in a direction of one members, then the other will become the zero force members. So for the last method is method of section. So the first step is we need to cut half of the diagram, which is truss, and then we can calculate it as a rigid body in the limits of equilibrium equation for a rigid body, which is the sum of fx is equal to 0 and the sum of Fy is equal to 0, and the last is the sum of moment is equal to 0. So that's all for me. Thank you.
Question for report. Given loads are shown on the roof truss, find the force in members DE, DL and ML. Based on the question, first thing first, we must find equation of Fy. Summation Fy equal to negative 7 plus 14 plus 14 plus 14 plus 14 plus 14 plus 7 plus Fay plus Fiy equal to 0. Summation Fy equal to negative 84 plus Fay plus Fiy equal to 0. Next, we must find moment at point A. Summation MA equal to Fiy times 48 minus 14 times 8 minus 14 times 16 minus 14 times 24 minus 14 times 32 minus 14 times 40 minus 7 times 48 equal to 0. Fyy equal to 42 and Fiy equal to Fay. After that, take a cut through the members DE, DL and ML. Work with the left part of the cut section. We get a equation of moment at point D. Summation MD equal to negative Fay times 16 plus 7 times 16 plus 14 times 8 plus FML times 6 equal to 0. And we get FML equal to 74.67 kilonewton. Next, we must find equation of moment at point L. Summation ML equal to negative FDE times 8 divide power source 65 times 9 plus 7 times 24 plus 14 times 16 plus 14 times 8 minus Fay times 24 equal to 0. And we get FDE equal to negative 56.6 0.44 kilonewton. Next, FML plus FDE times 8 divide power source 65 plus FDL times 8 divide 10 equal to 0. And we get FDL equal to negative 23.34 kilonewton.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fehman bin Muhammad Lokman and my matrix number is CD240095. And today I will be discussing the structural analysis of truss bridge designs, focusing particularly on the application of the section method for calculating internal forces. In our analysis, we selected the Pratt truss due to its exceptional track record in bridge engineering. Spanning over 2 centuries, its enduring popularity is attributed to its efficiency, simplicity, and reliability. The design is quite ingenious. It uses vertical members to bear compressive forces, while the diagonal members handle tensile forces, making it highly efficiency in mixed loaded scenarios where forces are distributed unevenly. We also compare the Pratt truss with other notable truss types to better understand the pros and cons of various designs. Pratt truss stand out for its straightforward design and cost effectiveness, making it a practical choice for many projects. The Warren truss excels in handling evenly distributed loads due to its repeating triangular framework, but can be less efficient for point loads such as concentrated weights in specific areas. The Baltimore truss is built to handle heavy rail traffic, making it robust and durable. However, the design is constrained by the need of intermediate support, limiting its use in longer spans. By examining these truss types, it's clear that each has strengths and limitations depending on span length, loading conditions, and structural needs. This analysis highlights the importance of selecting the right truss design to achieve a balance between stability, cost efficiency, and performance. Now let's move on to recommendations aimed at improving truss bridge designs for enhanced performance and sustainability. Firstly, material selections. It is crucial to use materials with high strength to weight ratios and an appropriate Young's modulus to withstand external forces, such as lift loads and wind forces, without unnecessarily increasing the bridge's mass or cost. This ensures the structure remains both efficient and economical. Secondly, design optimization. To improve load distribution, particularly for point loads, we recommend considering hybrid truss designs that combine the strength of different truss systems. Additionally, incorporating bracing and redundancy members can enhance structural support, minimizing stress concentrations and improving overall stability. Lastly, dynamic load testing. Current research often focuses on static loads, but real-world conditions involve dynamic forces like traffic surge, wind gusts, and even seismic vibrations. Conducting comprehensive tests under these conditions will provide critical insight into how the bridge responds to fluctuating and extreme forces, ultimately ensuring the bridge remains resilient under real-world stress. By addressing these key areas, materials, design optimizations, and dynamic testings, future truss bridge can achieve greater durability, efficiency, and reliability, meeting both modern engineer demands on long-term safety standards. Continuing our recommendations. For a simplified construction process, it is important to adopt streamlined methodologies that make the assembly of more complex trusses, such as Warren and K trusses, more efficient. By minimizing labor hours and construction times, we can significantly reduce costs in large-scale infrastructure projects while maintaining structural integrity. Next is sustainability consideration. Modern bridge designs should prioritize the use of environmentally friendly and recyclability materials that do not compromise strength or durability. By adopting greener materials, we can help reduce the project's carbon footprint and support long-term sustainability goals. Finally, routine inspections and maintenance. Establishing regular inspections protocol is essential for detecting early signs of buckling, fatigue, or joint wear. Implementing preventive measures helps to extend the lifespan of the bridge and ensures the safety of its users. By focusing streamlined constructions, sustainable materials, and proactive maintenance, we can create bridges that are not only cost effective and durable, but also environmentally responsive and safe over time. Thank you.